Hey everyone, and welcome. Today we're tackling a hard problem that combines a few different concepts. Find x sum of all k-long subarrays 2. It sounds a bit complicated, but don't worry, we're going to break it down step by step. Alright, let's look at what the problem is asking. We're given a list of numbers, which we'll call nums, and two integers, k and x. Our job is to look at every possible subarray of length k, calculate a special value for each one called the x sum, and return all of those sums. So what exactly is this x sum? It's a three-step process. First, for a given subarray we count how many times each number appears. Second, we find the x numbers that appear most often. And finally, we add up all the occurrences of just those top numbers. That total is our x sum. Now there's a really important rule for breaking ties. What if two different numbers appear the same number of times? The problem states that in this case, the bigger number wins. It's considered more frequent. So if 5 and 2 both appear 3 times, we'd prioritize keeping the 5s over the 2s. There's also one special edge case we need to handle. If our subarray has fewer unique numbers than x, for example, if x is 5 but our subarray is just 2, 2, 2, then we don't need to do any filtering. The x sum is just the total sum of all the numbers in that subarray. Let's make this concrete with the first example. Our list is 1, 1, 2, 2, 3, 4. And we're looking for the top two most frequent elements in a window of size 6. The first window is the whole array, so we count things up. We see 2 1s, 2 2s, 1 3, and 1 4. Okay, now we need to find the top two most frequent elements. The numbers 1 and 2 are tied, both appearing twice. Remember the tiebreaker rule, the larger number wins. So 2 is considered the most frequent, and 1 is the second most frequent. We keep all the 1s and all the 2s, and get rid of the 3 and 4. The sum of what's left, 1 plus 1 plus 2 plus 2, gives us 6. That's our first answer. The problem is that we have to do this for every subarray of length k. If the input array is huge, recalculating all the frequencies from scratch for each window would be way too slow. As the window slides one step to the right, we're only adding one new element and removing one old element. There must be a smarter way to just update our counts and our sum, instead of redoing all the work. Just a quick heads up. We'll be walking through the solution using Python. But don't worry if that's not your main language. The core logic is the same everywhere. I'll be showing the full code for Java, C++, and JavaScript towards the end of the video. The editorial's approach is really clever. It uses a custom data structure to keep track of our window. Imagine we have two buckets, or sets. We'll call them large and small. The large bucket will always hold the top x most frequent elements, the ones we care about. The small bucket will hold everything else. We'll also use a simple hash map just to keep a running count of how many times we've seen each number. To make the sorting work with our tiebreaker rule, we won't just store the numbers in our sets, we'll store pairs, or tuples, containing the frequency and the number itself. This way, our sets will automatically sort first by frequency, and then, for ties, by the number. Our goal is to always keep the large set containing exactly x of these pairs, and our data structure will constantly maintain the total sum of the elements in this large set. Okay, we've talked about the big picture and the logic. Now let's see what this looks like as actual code. I'll put the full solution up on the screen first. And don't worry, after that, we'll walk through the most important sections together. Alright, here's the Python code. It looks like a lot, but it's organized into two main parts. There's a helper class that contains all the logic for adding, removing, and rebalancing our small and large sets. Then, the main function uses this helper to perform the sliding window operation. We'll break down the helper class first. First, the initialization. When we create our helper object, we tell it the value of x. It then sets up our four key pieces of data: the frequency map, the two sorted lists for small and large, and a variable to track the sum of the numbers in the large list, which we'll call large sum. Note that this solution uses a library called sorted containers for an efficient sorted list, which is common in competitive programming. Now let's look at the add method. When a new number comes into our window, first we check its current frequency. If we've seen this number before, we need to remove its old entry, the one with its outdated frequency count. Then, we increment its count in our frequency map and insert it back into our sets with its new, updated frequency. That internal insert function is where the magic happens. After we update a number's frequency, we need to decide where it belongs. If our large set isn't full yet, the new item goes straight in. If large is full, we check if our new item is better than the worst item currently in large. Because it's a sorted list, the worst item is at the very beginning, If our new item is better, it goes into large and the worst one gets kicked out into the small set. Otherwise, the new item just goes into small. We always update our large sum whenever an item enters or leaves the large set. Finally, the main function puts it all together. It creates an instance of our helper data structure. First, it builds the initial window by adding the first k elements. It gets the x sum for this first window and saves it. Then, it starts the sliding process. For every other position in the array, it removes the element that's falling off the left side of the window, adds the new element from the right side, and gets the new x sum. So how fast is this solution? The time complexity is big O of n log k. That's because we iterate through all n elements of the input array, and for each element we might do an add or remove operation, which involves updating our sorted lists. That update takes log k time, where k is the size of our window, because the number of unique items in our data structure is at most k. The space complexity is big O of k, because our frequency map and sorted lists will store at most k unique elements at any time. Alright, that covers the main solution in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution in Java. It uses tree sets to act as our sorted sets. You can pause the video here to take a closer look at the implementation. Next up, here is the C++ version of the solution. This one uses std set for the sorted sets and std map for the frequency counts. Again, feel free to pause and review the code. And finally, here is the solution in JavaScript. JavaScript doesn't have a built-in sorted set, so a production-ready solution would need a more complex data structure like a min-heap and max-heap combo. This code shows the logic using simple arrays and sorting, which helps understand the flow even if it's not the most performant. So let's wrap it up. This problem is a great example of a hard sliding window question. The brute force approach is too slow, so the real challenge is figuring out how to update our answer efficiently as the window slides. The solution shows a powerful pattern, combining a hash map for fast frequency lookups with ordered data structures, like sorted sets, to maintain the top elements according to specific rules. Alright, before we jump into the other languages, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill. So I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems. So if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding and I'll catch you in the next one.